Green's theorem, divergence. Now, those of you who took physics 2 or are taking physics 2 will recognize something called the flux of a vector field. What's the flux of a vector field over region D? It's like this. If you have this region D and have some vector fields passing through it, you do the following scalar integration. What you do is at each point on the boundary, you talk about this unit outward normal vector. Unit outward normal. So I explained that normal means perpendicular, right? So you have a vector which is pointing outwards and perpendicular to the boundary. Okay? So you have the unit outward normal vector at each point. And what you do is you take the vector field dotted with the unit outward normal vector. Now let's think about what that means. If the unit outward normal vector and if the vector field on the boundary is going outward with respect to the domain D, is the angle between the two less than 90 degrees or more than 90 degrees? Let me repeat myself. If the vector field at a point is pointed outwards, is the angle between the N and F less than 90 degrees or more than 90 degrees? Less than 90 degrees. In that case, the dot product will be positive or negative? Positive. If it's less than 90 degrees, it's positive. Okay, so this is positive. Now let's look at this case where the vector field is going into the domain. The angle between the two, the n vector and the f vector, is greater than 90 degrees. Therefore, the dot product is negative. Okay. So this kind of measures whether the vector field is trying to go into the region or tries to come out. Okay. And then also you have to realize that dot product gives you what? Scalar or vector? Scalar. Okay. So this is a scalar quantity. To integrate a scalar quantity, we integrate by ds on the boundary of the domain. And because this is a scalar integral, it doesn't matter which way it's oriented. Okay? Yeah. It gives you the same value whether it's oriented backwards or this way. Okay? And what you want to do is, if you add this up, then you're kind of measuring the totality of this dot product, and it has the following meaning. If overall there's more vector fields coming out of the region, this flux will be positive. If overall more vector fields are going into the region, this flux will be negative. Okay? So in physics, you learn it as the following terminology. If the flux around D is positive, that means there's a source inside the domain D. Okay? So in the case of electric fields, you would have something positively charged in the middle, which makes this as a source. Okay? If this is negative, then you said this region D contains a sink. All right? So those were the terminology people used to talk about flux. And this talk about flux gave you a good idea about what the electric field is doing in that region. Okay. All right. So this is what we call the flux, and flux also has this additive property, meaning that if you have two domains which is sharing a neighbor, then when you do the integral around this one and this one, when you're doing this, the outward normal is that way, whereas if you're doing this, the outward normal is this way, and they're exactly the same and opposite. And therefore, when you do the flux of vector field F over domain D1, and you add the flux of vector field F over domain D2, then the middle one cancel, and you end up with the integral over the entire domain, which is same as the flux of F over D1 union D2. So it has this additive property. And additive property is exactly what you want if you want to reconstruct the flux from its parts. So what you want to do is, if you have a domain, just cut it into very fine, thin, small pieces. And each of these will have area dA times the density of flux, whatever that is. If you have this, then this additive property enables you to add them up, do the double integral, and reconstruct the flux of the entire thing. And the reason that this is also called the Green's theorem is because you have the same kind of thing going on. You have a single line integral equal to a double integral. Okay? It'll be a double integral. And to complete this theorem, all you have to do is to calculate the density of the flux, which is to choose a very small rectangle, HH, and you do A comma B, and you calculate this, this integral around this, and you'd have to divide by h squared and send h to 0. And that's a very long calculation, very similar to what we did for the circulation of vector fields. Okay? Should we do it?
No.
Of course not. Okay? So we're not going to do it. If you're interested, try to do it yourself. Maybe it'll feel like a big accomplishment. But anyways, this is what you're going to end up with. If you do that calculation, you'll find that the density of the flux is really L differentiated by x, m differentiated by y. That's the density of the flux. And by the way, this is what we called the divergence of F, if you recall. Okay? So we talked about divergence, curl, gradient, these operations you can do to vector fields and functions, right? And this is actually the divergence of F. And therefore, this is the revelation of the meaning of the divergence. When I first introduced to you divergence, I just told you how to calculate it. I didn't explain what it meant. The meaning of divergence is the density of the flux. And if you integrate this against dA with a double integral, then you have this identity. And this identity is called the divergence form of the Green's theorem. Now, this is usually referred with less importance. Some people just not talk about this at all. But and the reason is because this left side is not that interesting. You do f dot dr much more often than just something ds. So that's why this is used less. But still, it has some really important consequences in 3 dimensions. If you go to 3 dimensions, this is a similar theorem is called, goes by the name of Gauss divergence theorem. And it's very important in electromagnetics and also fluid dynamics. Oh, by the way, in fluid dynamics, when you talk about incompressible fluids, if the fluid is not compressible, what do you think the vector field will look like over a region? What will be the flux around the vector field going through a vector? What's the flux of a vector field going through a region D? If it's incompressible, it can't be compressed.
0?
It'll be 0 because if more things were flowing in, what's going to happen to the fluid inside, trapped inside? It's going to, I mean, more fluids are going in, so it'll be compressed more, right? The only way you can have a negative flux on a region is when you have a negative value for, when the fluid can be compressed, okay? So one important equation that you're going to use in fluid dynamics is that if you have an incompressible fluid, you say the divergence equal to 0. This is the 2-dimensional divergence. If your vector field is 3-dimensional, say LMN, then the divergence of F is differentiate the first one by x, second one by y, third one by z, and you add them up. And the three-dimensional fluid dynamics equation will contain one of the equation as divergence of that velocity vector field at 0. Okay, so that's pretty important.